we're on 6.4. Sorry. Right. Okay. 6.4, we are going to talk today about, I think, inverse functions. Yes, using inverse. Okay. Yes, you're gonna have to graph probably. Okay, inverse relationships, an inverse relationship, okay? An inverse relation is interchanges the input and the output values. Meaning, if my original relationship was I input 0, 1, 2, 3, and 4, and I get 6, 4, 2, 0, negative 2 out, my inverse function should be opposite of that. My inputs are now what were my outputs, and my outputs are now what were my inputs. So, my inputs are 6, 4, 2, 0, negative 2, and my outputs are 0, 1, 2, 3, 4. Okay? It flips it. It makes it opposite of what it was. So when I have an inverse relationship, I'm essentially flipping things around. Okay? The inputs and the outputs flip. See how the center ones, though, repeat because it would be exactly opposite. Okay. So, we're going to talk about finding inverse relationships. It says, find an equation for the inverse of the relation y equals 3x minus 5. There are 2 steps to solving for inverse functions. The first step is you switch x and y, and the second step is you resolve for y. So, I'm literally going to take this equation and I'm going to say x. I don't like this new setup. Well, I don't know what just happened. I don't think this is working. Okay, so you're gonna do it this way. You're gonna say x equals 3y minus 5. And you resolve for y. So I add 5 to both sides, I get x plus 5 equals 3y, and I divide by 3, and you get y equals x plus 5 over 3. There is the inverse function of y equals 3x minus 5.
Kobe.
Okay, so you have to switch x and y and resolve for y to get your inverse function. This is where compositions come into play. If you plug an inverse function into the original function, the answer you receive should be x. If you plug a function into the inverse of itself, the answer you receive out should be x. That's how you know that they're actually inverses of each other. So if they say prove that these 2 functions are inverses of each other, if they don't come out to give you the answer x, then they're not inverse functions of each other. So the way we represent inverse functions is by this sign right here, f to the negative 1. You read it as the f inverse, or the inverse of f. Okay? So when you see that, that means that you're working with the inverse function already. Okay, not the original function, the inverse. So, we are going to see if these are inverse functions of each other, which means we have to do 2 separate sets of equations. Okay, the first equation we need to do is we need to take the one that I underlined in red, the f of x, which f of x equals 3x minus 5. And we need to take the inverse of that function, the f inverse, and we need to plug them into each other. So, first I have to say the function of the inverse function of f of x. I have to solve it this way, meaning I'm plugging the green equation in to the x of the red equation. So 3 times 1/3 x plus 5/3 minus 5. What is 3 times 1/3 x?
1x.
Yeah, or just x. What is 3 times 5/3? Yeah. 5, because 3 times 5 is 15, divided by 3 is 5. So I get x plus 5 minus 5, so you get x. So it checks out that way. Now we have to check it out this way. To prove they're inverses of each other, you have to do both equations, the inverse function of f of x. So now we are plugging the red equation in to the green x. So I have 1/3 times 3x minus 5 plus 5/3, yes? Okay, so what is 1/3 times 3x? X. What is 1/3 times negative 5? Negative 5/3. Plus 5/3, and you get x. So these two equations are the inverse of each other because both ways that we plug them into each other, you get x out.
So you should get an x, not no.
Correct, always. Okay. Elastic bands can be used in exercising to provide a range of resistance. A band's resistance, R in pounds, can be modeled by the formula R equals 3/8 L minus 5, where L is the total length of the stretched band in inches. Find the inverse of the model. How can I find the inverse of that model? Flip what?
The R and the L.
Flip the R and the L, and then solve for what? R. R. Because right now it is solved for R, so you're gonna re-solve for what it's already solved for. Okay, so now, what do I do from there? Add 5, L plus 5 equals 3/8 R. Now what? Multiply by the reciprocal, 8/3. Okay, 8/3. So you get 8/3 L, right? And then 8 times 5 is 40. So plus 40/3 equals R. Boom. Use the inverse function to find the length at which the band provides 19 pounds of resistance. Okay? So what am I looking for? It's for L, so I'm plugging 19 into R, correct? Okay. So then I'm gonna subtract 40/3 from both sides, correct? You get 8/3 L equals, I don't know, 19 minus 40/3, 5 2/3. And then you have to multiply by 3/8, right? So then L equals 2.125. And that would be the length, correct? Inches? Is that what it, I don't know. Inches, yeah, inches. Okay, so you're gonna solve problems like that. Inverse of nonlinear functions. I should have get this off of there, but see that? Okay. The graphs of the power functions f of x equals x squared and g of x equals x cubed are shown below. So this is x squared right here, this is x cubed over here, okay? Are shown in the lines, y equals x, the reflections are, okay? So see this dotted line coming across here? They took this graph right here, the blue one, of x squared, and reflected it over that line, and you get this red graph, okay? They took this blue one here and reflected it over that diagonal line, and you get this red graph. Okay, it says, notice that the inverse of g of x equals x cubed is a function, but that the inverse of f of x equals x squared is not a function. Why is this not a function?
Cause the two things include
Because what, Chris?
there's 2 points on the same line.
Yes, because if I do a vertical line test, like this black line shows here, if I do a vertical line test, it crosses through there twice. So it's not a function, okay? So if the domain of f of x equals x squared is restricted to only non-negative real numbers in this case. So when this happens here, this reflection of this original one is restricted to just non-negative real numbers. Because when I reflect this portion, okay, I will only get this portion of the red, okay? And when I only get that portion of the red, it's technically a function because I don't have a linear line going through it. I don't have a line going through it vertically. So, find the inverse of f of x equals x squared, where x is greater than or equal to 0. Then graph the function and the inverse function. So how do you graph x squared, first of all?
That's an parent graph.
That's a parent graph. So it should just be a parabola, correct? Okay, so it should be what we saw on that first slide just now, like this, yes? Okay, so my parent graph. Now, if I want to then graph the inverse of that function, and it says x is greater than or equal to 0, that means I can only plug in numbers that are greater than or equal to 0. So, if I plug in, so I have to first solve for the inverse function. Right now, it's set up this way, correct? So when I solve the inverse of that, that means I switch these two, yes? And resolve for x, or for y. So I get this, the square root of x equals y. What's the square root of x function look like when graphed? Put some numbers in there and tell me what you get out. If you put 0 in, what do you get out? 0. If you put 4 in, what do you get out? 2. If you put 9 in, what do you get out?
3.
Okay. So look at what happens to this graph. It should curve.
Is it the not function?
Yes, because it would be the not function if I didn't have that parameter on there of x is greater than or equal to 0. Because then this would reflect down over here, yes? Okay, so I can take portions of things so that I can create functions. Okay, horizontal line test. The inverse of a function f is also a function if and only if no horizontal line intersects. So we've talked about vertical line test, but now also horizontal line test comes into play on the original function. Meaning, if I drew a line through this original graph here, like this, I would know that its inverse is not a function. Because when I draw a horizontal line, it goes through there twice. So if it goes through the original function twice horizontally, you're not going to have an inverse function. Does that make sense? Okay? So I don't have to graph it first. I can actually draw a line first and then test from there. Will this graph have an inverse function?
Yes.
Yes, because if I draw a horizontal line through there, it's only going to go through there once. Yes? How do I find what that inverse function is? So, switch y and x. So currently it says y equals 2x cubed plus 1. Okay, so we're going to switch these two. So I get x equals 2y³ plus 1, now what? Subtract 1, x minus 1 equals 2y³, now what?
Divide by 2.
Okay, and y³ equals x minus 1 over 2, now what?
Take the cube roots.
Take the cube roots, good. So then I get the cube root of x minus 1 over 2 equals y. There is the inverse function. The way your book is going to write this, they're not gonna put a y there, they're gonna put this there. Okay. To represent it like that. So you have to show me work tonight, yes? Okay. The average price P in dollars for a National Football League ticket can be modeled by the formula P equals 35T to the 0.192, where T is a number of years since 1995. Find the inverse model that gives time as a function of the average price ticket. How do I do that? What is it that I actually want to solve for in this new equation? T. So what do I need to do then?
Switch P and T.
Yeah, because I want to find the inverse of this function, so switch
Excuse.
P and T, what?
Look, can you put y instead of f? Exponent -1.
You can, but I'm telling you, they're going to start putting f to the -1 as what it's represented by.
Oh,
Okay. So switch P and T. So let's switch P and T so that I get T equals 35P to the 0.195, that's what you wanna do?
That's what you think it is.
Okay, but look, it says, modeled by this, where T is the number of years since 1995. Find the inverse model that gives time as a function of the average ticket price. It just wants time as the function of the average ticket price, correct? Right, yes. So if I switch P and T and resolve for P, well, we can try it this way. I don't think it's gonna work this way. You would divide by 35, yes. How do you get rid of this?
Radicals that, they're not squared, they're 0.195.
Oh, it says 9.2, doesn't it, there? There's an easier way to get rid of that.
You just put the exponent on the other side.
Because that would be a weird route to take, correct? Like, we can't really plug that in. So how do you get rid of a power? How would I get a power to be 1 up there? How could you get it to say P to the first? What would you have to multiply 0.192 by?
1
Not by 1, by 1,
over 0.92.
by what?
1 over 0.92.
Yeah, 1 over a point. So if I raise this, okay, to the 1 over 0.192, that gives me 0.192 over 0.192, which is 1. So I get P to the first. And over here, I'm gonna have to raise it to the same thing, yes? Okay? Okay, so then you get that. And what is 1 divided by point 192? It's 5.2. So I actually have this going on, I'm gonna change it. Cause when I divide that by that, I get 5.2, okay? So I get this formula, okay? That is now my inverse function, okay, of that model. That's all I need. Okay, that's now my inverse function, and then I can solve from there. So, you have to show me lots of work tonight, even if it's simple arithmetic, because I want to see you do